And I probably massacred your name there, so I apologize.
That's all right. It's pretty common. Okay. All right, thanks. So yes, today I'm going to be talking about the LDEX operations with respect to meteor streams at the moon. So we've already seen this. I'll just briefly summarize again. LDEX is this bowl-shaped instrument that's flying through, somewhat collecting the dust. Whenever we have a grain impact this bowl, it creates an impact plasma and we can read out properties of the grain. So here's a plot we were just looking at. Shown on the top, again, is every minute how many impacts we got, and on the bottom is a day average. And what we notice is that there are times that we see a significant enhancement in the impact rates. So not only do we see an enhancement, but they happen to be timed at the exact time that there should be a meteor shower hitting the moon. So I've highlighted 5 here, but we're going to talk about a couple more. The main one that you can really see is the Geminids, and we're going to spend a little more time talking about that. So it turns out that we didn't just see, usually our impact rates are a few per minute, and during the meteor showers, it wasn't just we went from a few per minute to like 10 per minute. We would see sometimes 100, 1,000 in 10 seconds. So here's an example of one such event where we're kicking along and we have an impact every minute or so, and then all of a sudden we get about 100 impacts in 10 seconds. And so these events we call bursts, where we just see an incredible amount of dust impacts. And what we think is going on is that we're actually flying through an ejecta plume. So during a meteor shower or during any time throughout the history of the moon, it's being constantly barraged by impactors. And when you have an impactor, it kicks up possibly hundreds to thousands of times its original mass of material from the lunar surface. And we think that we're actually getting lucky and we're flying smack through those. And that can tell us something about the meteor showers. So, well, we do have a coincidence in time with the impact rates and the bursts. It's not enough just to have temporal correlation. We wanted to see if geometry was at play here. So we performed a test to see if we're really seeing meteor streams or maybe there's some other event that's correlated that's messing up our data. To do that, we introduced 2 criteria, after which we would say it's most likely a detection of a meteor stream. The first one is that there should be no burst detected on the opposite side of the moon. So here's a little diagram of the moon. If we have a meteor stream coming in from a particular radiant, it's going to bathe one full hemisphere of the moon. And if we saw a lot of bursts on the other side, then it's probably not having to do with that meteor stream. So we want to ensure that we only see them at the right side. The other criteria is that not only do we see them on one side, but they have a geometric preference. So right here, you can imagine the sub-radiant point, if you will. There should be a lot of stuff kicked up because the meteor stream is hitting the moon smack on. But if you go out as a function of angle from that radiant, you would expect to see less and less. You'll definitely see a single cosine just from the effective area that you're going to be hitting, but there's a little toy model that suggests that you actually might see a cosine cube dependence, and so we'll talk about verifying that later. But for right now, we'll just assume that's the function and go forward. So the easiest one to test was the Geminids. It was our strongest performer, and it's actually one of the streams that we understand the best. So here's a nice cartoon of the Geminid stream from this Berenstain and a very difficult name to pronounce, 2006. And you can see everything is right-handed, and some meteor streams we hit both of their nodes, but in the Geminids we only hit one, and it's this one. It goes into about 1/10 of an AU and out to 2.5. And so we have these orbiting debris, and we're going to smack into the side of it with Earth and the moon, and it's going to shower the moon with meteoroids. Not only do we know where it is, but we know when it happens. This is one set of observations. These are by eye, but there's also meteor observations that says it peaks very sharply. So these are roughly days of solar longitude, but similar. And it decays very fast within plus or minus about 1.5 days. And so that's what we're going to be using, this 1.5 days within the meteor window. So then we can paint the radiant target onto the lunar surface. So this bullseye is the center of that is where the meteor the stream hits the moon, and then these angles show both the angle on the moon from the radiant and also the angle of incidence from normal that the meteoroids are going to be hitting the moon, and it's colored by cosine cubed. And once we have that, this is our predicted mass production, the amount of stuff that should be kicked up. Then we can overlay the LADEE trajectory on top of that. So this is for the plus or minus day and a half from the time of maximal flux from the Geminids, and only times that LDEX, our instrument, was on. And so this red ribbon is where we would expect the majority of the stuff to be kicked up. So again, the color is the amount of plumes that we think should be generated. And you would expect to see these bursts cluster around that. And it just so turns out, when you look at where the bursts happen, it's dead on. It's like a bullseye. They're painted right where we would expect. So we have the highest number of bursts. This is qualitative now. We'll get into it a little more later. But you see a lot of dots here on the red, less dots on the blue. And that's what we were really hoping for. And that was a nice sanity check. So this met criteria 1. They cluster. And there's none on the other side of the moon. All right, so the second criteria was not only should they be on one side, but you should see more when we predict higher mass production. So if we're right in the bullseye, you should see more dust and bigger dust, because the more plumes you have, the more chance you're going to measure a big grain. And so this wedge kind of bite out shows you that as a function of the theoretical mass production, or the number of plumes that we think we should be seeing, we see more. So this histogram shows that you have a lot more stuff when we think there's more plumes than when there's less, and that there's bigger grains. So this is radius on the x-axis, and there's bigger grains at higher mass production, and there's this bite out where you don't see big grains at low mass production. So this satisfies criteria 2, and we can say that we think we've detected a meteor stream by this criteria. So returning back to this impact rate plot, you can see that there's a couple more lines on here, and actually there's like a bajillion meteor streams, minor, major, some by different observations. There's radar, there's by eye, but we really looked at pretty much every meteor stream possible within this window. So I'm going to point your attention to another one. There's two. This one's really strong, the Quadrantides as well, and you can see a peak. But the question is it just a coincidence, or is this geometrically validated? So it turns out that it does cluster just like we would expect. The Quadrantides hit high, but right where this ribbon of high mass production is where we see the number of bursts, which is great. So all in all, there are about 8 meteor streams that satisfied both of these criteria. I do want to point out that the Geminids was really the one that was significant. It was statistically significant in the number of ejecta plumes. The rest satisfied the criteria, but on average, we have that many bursts, say within 3 days. It's just they don't seem to cluster as nicely. But the Geminids are the real ones that were the strong performers and are unambiguously identified as a meteor stream. So the last thing we've done is to verify check if this was a good assumption. So it's pretty neat. We get to use the moon as this big experiment. Mother Nature set up an experiment that we can't do on our own, and that's shoot a huge collimated beam of particles going tens of kilometers per second at a very, very large body and see how the body responds. And so we wanted to test and see, was this a reasonable assumption? And so it turns out it is to first order. So what this shows is the impact rate as a function of angle from that subradiant point. And what you would expect, if I just picked a random place on the moon, this should be a flat distribution. There should be no preferred angle. They should all be coming from roughly every direction. However, we see there's a lot more at low angles than there are at high, and when you fit a cosine, it's within some large error bars, it's not inconsistent with a cosine cubed. So there's a lot more to be done on that, but in conclusion, what we found out is the moon is very sensitive to meteor showers, and Mother Nature set up this beautiful laboratory for us to do these large-scale experiments. And now that we've learned how the moon is starting to respond to these meteor showers, we can use this when we go to other airless bodies. So say we were orbiting we were orbiting not the moon, but maybe we were doing flybys of Phobos and Deimos, and you see a clustering of events during a time that we didn't know there'd be a meteor shower, then it's possible we'd learn something about the meteor environment of another body. So that's where we are now, and thank you for your time.
John Keller, Goddard. I'm curious about the velocity of the dust particles that you're seeing coming up. Are they energetic enough to escape? And perhaps maybe something you might see on the opposite, the antipodal side, where if they go into a half orbit or so?
Yeah, that's a great question. That's something we're actually still actively working on. So right now, we usually assume that we catch them right when they start falling back down. Just probabilistically, if they're at their turning point, that's the most likely time to get them. But within our data, we can get a speed out, and they look really fast. And so we're trying to rectify that right now. So I unfortunately don't have a solid answer for you on that one yet, but we're working on that.
More questions? Just one from me. What does really fast mean, roughly?
Over escape speed, so anything over 2.5 kilometers per second, and sometimes we see things that may indicate they're significantly faster, and we're trying to figure out how that could be.
But you're not talking 20 kilometers a second?
No.
Okay. Well, thank you very much.